In section 8.2, we are going to continue our talk about the inverse trigonometric functions. In 8.1, we talked about inverse sine, inverse cosine, and inverse tangent. And kind of the big bulleted point items that we need to remember is that regular trig functions operate on an angle and have output values that are essentially ratios of ratios of sides of triangles. So we have that the trig functions operate on an angle, so that tells me that's the input, okay? And then we have output values that are essentially ratios, okay? Now, on the flip side of that, when we're dealing with the inverse trig functions, the inverse trig functions operate on a ratio and have output values that are angles. Okay, so in the situation of an inverse trig function, your input is a ratio and the output is an angle. But here's the thing, when we were looking at those initial trig functions, we found that none of the trig functions are really what we would call one-to-one functions. So that means that in order to have an inverse that is also a function, you have to make sure you start with a one-to-one function. So because none of the trig functions are one-to-one initially, we essentially restricted the domain of the original trig functions so that we had a segment of the trig function that was one-to-one. And then from that, we built our inverse trig functions. So when you have these inverse trig functions, yes, they operate on a ratio, meaning the input value is a ratio and the output value is an angle, but it has a very specific interval for the domain. But be mindful of the range for the output, okay? So remember, we restricted the domain for the initial trig function, which meant when we built its inverse, the domain became the range, and so we have this restricted range for our trig, the output for the trig functions, okay? So just as a quick reminder, when we're talking about inverse tangent of x equaling theta, we have to have output values that are between negative pi over 2 and positive pi over 2. So like on the unit circle, we're kind of looking at Q1 and Q4, so quadrant 1 and quadrant 4. The issue here is we can't for tangent inverse or inverse tangent be exactly negative pi over 2 or exactly pi over 2 because at those values tangent would be undefined. So as long as we're between negative pi over 2 and positive pi over 2, not including those endpoints, we're good. Now, for sine, when we restricted our sine function, we said, hey, let's look at the segment of sine that just goes from negative pi over 2 to positive pi over 2. So now when we look at the inverse sine function, the values that we get as outputs must be in this range of negative pi over 2 to positive pi over 2. So again, Q1 and Q4 or quadrant 1 and quadrant 4, but we can include the endpoints here. So the exact value negative pi over 2 and the exact value positive pi over 2, they're okay for inverse sine. Now, inverse cosine is a little bit different. When we looked at inverse cosine, if we look at inverse cos, or if we just look at cosine, if we look at cosine from negative pi over 2 to positive pi over 2, we have a segment that's not one-to-one. And remember, when we looked at those initial trig functions, we needed to look at a segment of the initial trig function that was one-to-one. Okay, so when we looked at cosine, we had to change our restricted domain for cosine, and we had to look at it from 0 to pi. So that way, when we look at the inverse cosine function, we're limited, okay, in our range of outputs. So our angles, when we're doing inverse cosine, have to be from 0 to pi, which puts us on, like if we're looking at the unit circle, that puts us in quadrant 1 and quadrant 2, okay? So just be careful, cosine's a little bit different, okay? So the first thing we want to look at is composition of trig functions. And we kind of looked at this when we were in 8.1. We were looking at if we compose a trig function with its inverse or compose the inverse with the trig function, they'll essentially unravel each other as long as we're very cautious with the domain of the input function. Well, in this section, we're going to look at at two functions that are not inverses of each other. So what do we do? Okay, so you can see here at our examples, we're going to look at cosine of inverse tangent, and then we're going to look at tangent of inverse sine. Well, cosine and tangent aren't going to undo each other. They're not inverses of each other. Tangent and inverse sine are not going to undo each other because they're not inverses of each other. So we have to find a new way to approach composition of trig functions when we're looking at two functions that aren't inverses of each other. So we have some steps listed out. What we're going to do is we're going to draw an angle theta in a very particular quadrant. So we have to be very mindful of our quadrants. So remember, when we're talking about inverse tan, we're talking about quadrants 1 and 4. When we're talking about inverse sine, we're talking about quadrants 1 and 4. And then cosine or inverse cosine, we're talking quadrants 1 and 2. Okay, so we draw an angle theta in the correct quadrant. We find all of the sides of the resulting reference triangle. And then we find the desired trig function using that triangle. So let's dive in. So these are going to feel a little weird, and that's okay. It's okay if things feel weird at first, but hopefully we'll get you squared away to where you don't feel so wild about this. So for example 1, it says find the value of each of the following. And for part A, we say find the value of cosine of inverse tangent of 3/4. Well, what in the world do we do? Because cosine and inverse tan, they're never going to just like unravel each other, okay? So we have to think about this, okay? So first of all, let's make note of the input here. So when I make note of this input, I'm saying I'm looking at tan inverse of 3/4. So I know that this innermost input is a ratio. And when I find inverse tan of this ratio, the result I get is going to be some angle theta. So essentially, if I have inverse tan of 3/4, it's going to be some angle theta. So that's what I can do. I can start by saying, okay, let's let theta equal inverse tan of 3/4, and then essentially all I'm doing is finding cosine of some angle theta. Well, that's not too bad, right? We could do that, okay? So let's go ahead and think about this. We know that when we're dealing with inverse tangent, we have to be somewhere in quadrants 1 or 4, because this is where we have negative pi over 2. This is where we have pi over 2, okay? And this right here, this 3/4, that tells me that I'm looking for where tangent is positive. Now, tangent is positive in quadrant 1, but negative in quadrant 4. Okay, so that tells me that this angle theta that I need to build and then essentially build this reference triangle, I'm going to need it to be in quadrant 1. Okay, so let's go ahead and do that. So in quadrant 1, I know I'm looking for some angle theta that when I build my reference triangle, I know that tangent of that in that particular angle is going to be 3/4, because remember, let me scoot this up just a smidgen so we have a little bit more room. There. Okay, so I know that if I have tangent or inverse tangent of 3/4 equaling theta, I could think of that as really, well, if I take tangent of some angle theta, the ratio would have to be 3/4, okay? So we know that with this particular triangle that we've drawn, we've got some angle theta, and we know the ratio for tangent would have to be 3/4. And remember, tangent is opposite over adjacent. We learned that in like section, I don't know, like 7.2 or something, okay? So if I build this triangle that has this angle theta, the side opposite of theta has to have a length of 3. The side adjacent to theta would have to have a side length of 4, okay? So what I need to do is find the third side right here. Well, we've done that several times in this course. We just need to look at the Pythagorean theorem. So the Pythagorean theorem says c squared equals a squared, which we're going to call 4, so 4 squared, plus b squared, which we're going to call b3, so 3 squared. So that tells me I get c squared equals 16 plus 9. So c squared is 25, which then tells me that if I take the square root of both sides, c on this reference triangle has a length of 5. Okay? So we've done quite a bit here. We've acknowledged that we're looking for cosine of inverse tan of 3/4. Well, inverse tan of 3/4 is going to have an output that is an angle. So essentially, if we say, let's let theta equal tan inverse of 3/4, then we can just essentially find cosine of that angle. Well, we had some building to do because we know that if we have inverse tangent of 3/4, that 3/4 is some ratio that's going to spit out some angle. So if we can think of tan inverse of 3/4 equaling theta as tangent of theta equaling 3/4, that gives us the ratio for this angle theta that we need to use when we build our reference triangle, which we have now done, which we know needs to be in quadrant 1 because this ratio for inverse tan is positive, tangent's positive in quadrant 1. And remember, tangent, inverse tan, we're limited to quadrants 1 and 4, okay? So when we build this triangle, we have to find all three sides. We know that the side opposite of theta has to be 3. The side adjacent to that has to be 4 because of this right here. We know that tangent is opposite over adjacent, and so we had tangent equaling 3/4. We use the Pythagorean theorem to find our missing side, which is 5. And now using this triangle right here, we have enough information to figure out what cosine of theta is. Using that very same theta, we can say, well, cosine is the adjacent side over the hypotenuse. So that tells me that cosine of theta is going to be, well, 4/5. So when I finally take cosine of inverse tan of 3/4, I realize that I'm just taking cosine of the same angle that has a tangent ratio of 3/4, and that gives me cosine of theta equals 4/5. Okay, so the answer to part A is 4/5. Okay, now let's look at example B. Okay, so example 1, part B is what I should say. So we have kind of a similar situation here. We want to find the exact value of tangent of inverse sine of -2/5. So let's think about this. Sine inverse or inverse sine of -2/5 is going to have some output that is some angle theta, okay? Because I know that inverse trig functions have an input that is a ratio and they have an output that is an angle, okay? So if I kind of rethink this whole thing and I say, okay, let's let theta equal this input right here, this sine or inverse sine of -2/5, then if I can figure out what that theta is, I can essentially just evaluate tan of theta, okay? So we got some work to do. All right. Now I know that sine inverse or inverse sine is limited to -pi/2 to +pi/2, which on the unit circle puts me in either quadrant 1 or quadrant 4. Okay. Well, this ratio right here for inverse sine is negative. So that tells me this ratio for sine is going to have to be negative, which puts me in quadrant 4. Because in quadrant 1, sine is positive. It has positive ratios in quadrant 1, and sine has negative ratios in quadrant 2. So that means when I build this triangle, this angle theta, and then the resulting reference triangle, I need to build it in quadrant 4. Okay, so let's look at that. Alrighty, so if I'm looking in quadrant 4, and I have some angle theta, okay, when I build my triangle, I know my angle theta is right here, okay? And then if I can think of inverse sine of -2/5 equaling theta, then I can rewrite that and think, okay, using just regular old trig functions, that tells me sine of this angle theta is going to have a ratio of -2/5. And remember, sine of theta is always the opposite side over the hypotenuse. So that tells me the side opposite of theta has to be -2, and then my hypotenuse has to be 5. So what I need to figure out is this missing side, which is the side adjacent to theta. So we can just use the regular old Pythagorean theorem. So I know what c squared is. That is 5. So I get 5 squared equals the adjacent side squared, which we don't know, that's a, plus the opposite side, which we're going to call it b squared, which is -2 squared. So 5 squared is 25, a squared is just a squared, and -2 squared is 4. So let me see if I can give myself a smidgen more room. Okay, so let's see, we want to solve for a squared, so I need to start by subtracting 4 from both sides, which makes this 21 equals a squared. And if I take the square root of both sides, I get that a is equal to the square root of 21. So this side up here is now the square root of 21. Okay, so we used a bunch of information. We've done quite a few things here. Okay, we were able to draw an angle theta. We acknowledged that theta is going to have some ratio of -2/5 as far as sine is concerned. So we built our angle We built our reference triangle. We found all the different sides of our reference triangle using that ratio for sine and then the Pythagorean theorem. And all that's left is to acknowledge that, hey, we know what theta is, essentially. So we can take tangent of that same theta. And remember, tangent is opposite over adjacent. Well, using this reference triangle, we have that the side opposite is -2, and the side adjacent to theta is the square root of 21. Well, it's -2 over square root 21, which at this point, hopefully, you know, needs to be rationalized. So we rationalize, and tan of theta, eventually we get is -2 root 21 over positive 21. Okay, so it takes a little bit of work, but when you do composition of functions where you have two different functions that are not inverses of each other, a little more work involved. You have to really think about what is your input. Is it a ratio or is it an angle? And then you can kind of build out from that. Okay, so that is topic 1, composition of trig functions that are definitely not inverses of each other.